Hello, a great welcome to Idea Statica tutorial. Myself is Jarajan P. This is tutorial number 7. Here I will demonstrate how to model and design an end plate bolted moment connection. The example connection used in the tutorial is shown here. We will discuss how to verify this joint for a given set of design loads and also obtain its design resistance. So let us start Idea Statica tutorial number 7. So in this example, we'll start importing a suitable model available from the connection wizard. So let us start first of all filling these parameters details. So here I will write down this is my extrusion structure, and let me mark the description as the moment connection. This is my MC1, I will call it MC1, and we'll keep the material grade as S275, and the bolt assembly will be M24 8.8, and the concrete grade it is will keep the same, and the design will be done as per the European code. And now let us start selecting a suitable end plate moment connection model that is available from the connection wizard. So let us just see what are the models available. I think that this will be a suitable model which we can later modify, okay, to suit our requirements. So let us create the project. So this is our model. So let us start editing this model for the column sizes and for beam sizes and for the various manufacturing operations involved. So let us start with the column. So in the column, okay, we find that it is the standard model has come with a European section. So let us start modifying it for the UC. So we'll add X section, and here we'll write. So this is for the column. So would like to have a UC section. So this is my UC, and under the UC we can select 254 by 254 by 107. So we have selected it 254, okay. So and the material will be S275, okay. So and all other parameters will remain the same, okay. All these angles will remain the same. So we need not to change anything in the column size. So now let us go straight to that B1, and the B1 again we find that's a European section. So let us change it to a UB section. So we'll just add here, add button, and then we'll go for the UB section, or okay. So we can go for the UB, and this is my UB, and in the UB we will select a 533 by 210, 533, yes, by 210 by 92. So we can have it as 533 by 210 by 92. So this is our beam section, okay, and we'll press okay, and all other parameters will keep the same, okay. So there are no changes in the parameters, and now let us do one thing. Let us start modifying the other member B2, and the member B2 obviously will keep the same as the B1 here in this tutorial. So let us start editing it. So here again we'll use the same UV profile. So we can just add it, or we can also copy it directly from B1. So here we can just press it, and we can select the UV section. So it's my UV profile, and we'll select the same section, that is a 533 210. So 533 210 by 92 by 92, okay, it's okay, fine. So we have kept our column sizes and the beam sizes as per our actual situation. Now is the time that we start editing the required manufacturing operations. So here let us start with the EP1 operation. So a number of operations have already come along with that, the model available from the imported from the connection wizard. So whatever we require, we'll keep it. Others, let us for the time being, let us keep it off. Okay, we'll keep all this off. or we can later delete it. That is not an issue. So let us start changing the the EP1, that is all the parameters associated with the end plate. This is my end plate that is already connected. So let us just change it. So obviously this is connected to, as we know, it is the member 1 will be my beam B1, that is correct, and member 2 will be my it is a B2. So here I want that end plate to be generated both for B1 and B2. So we'll keep member 1 and member 2 as B1 and B2, and it is connected to the column C. And we have the member as the material property will be as 275, and the thickness in this case will keep 25 mm. So this is 25 mm, and the connection type will be the bolted, and we'll keep it as the dimensions. Now we need to first of all mention the dimensions of this end plate. So we'll choose it as the profile to profile. That means with respect to the profile edges, we'll fix the dimensions of this end plate. So let us keep the top one as 90, that is as per our requirement. So as we start modifying these dimensions, you will find that the corresponding changes simultaneously takes place in the model in the GUI. So let us keep the left dimension as 21. Remember, these are all the pre-calculated dimensions. So, and the bottom one, let us keep it as a 37. So this is my 37, and the right also will keep the same as the left, that is my 21. So, and we don't require any backing plate here. So we'll remove it. So we have finalized all the dimensions of the end plate. So we have it as so these are the important parameters. That's the top is 90, and my bottom is 37, and the left and the right are 21 each. So the definition of the end plate size is complete. So let us now start populating the layout of the boards. So here we have the boards, that's the type M24.8, will not change it. Let us start fixing the layout for the top layers. So here we'll keep it as the top layers as so we'll keep it as minus 150. These are all the pre-calculated dimensions, 150, and then we have got the 90, and then we have the 100. So you can see that correspondingly the changes have already taken place in the top layers. We have populated 3 rows in the top, and the left layers, we'll keep the left layers at say minus 55. So this dimension will give the position of the rows, so minus 55, and the bottom layers will keep it as at minus 60. So this will keep it as a minus 60. So you can see that it has slightly moved up, and the right one will keep it as a minus right layer as minus 55. So minus 55. So that completes the definition of our arrangement for the structural bolts. So it is important that these dimensions are to be properly verified. So it is minus 150, 90, 100, and the left layers we have got a minus 55, and the bottom is minus 60, and the right is minus 55. So now let us provide the dimensions of the flange welds as well as the web welds. Means the weld size that is required to connect the flanges to the end plate, and also the weld size required to connect the web to the end plate. Obviously here we'll use the double-sided fillet welds. So let us start providing the dimensions. So here I will use say 10 mm. So we'll increase this flange portion which directly transfers the moment. So this may require a larger weld size. So it will keep it as a 10 mm, and this is double-sided. And let us provide a slightly lower one for the web, that is let us keep it as a 6 mm. So this is my 6 mm, and this is a fillet welds on both sides. So as we do not require other operations, let us start deleting these operations. So we'll select the stiffness. So these are the stiffness plates will not require for this tutorial. We'll simply delete it, and this also will delete. and we'll delete. So we can delete all other details because this is a model which we have taken directly from that wizard. So all these details may not be required for us. So we have deleted all these details, and now our model looks to be very simple. So let us see the model that is generated here. So you can see that this is the arrangement. Okay, as you can see on the top we have got 3 rows, and the bottom I have provided only 1 row, and basically the tutorial models a case wherein the beams are subject to only gravity loads. So that could be the reason why you will find that the bolts are not symmetrical, and at the same time you will find one very important thing, that is in this case, let me just rotate it. Yes. So in this case, when you apply a moment, the top flange under gravity load, it will be under tension, and correspondingly the top rows of bolts will be under tension, and the bottom row will have a very negligible tension. It is essentially used when we use the hand calculations. We essentially make use of the bottom bolts for taking the shears. So that is all about the model. So let me just rotate it so that you can see. So these are the connections. So we have got the same beam size on both sides. So you can see that all the components are properly connected. We have got a proper weld assembly, and we have got totally 8 number of bolts for each beam. So having done that, let us straight away go for the load effects. So we will check this connection for a shear of, let me say there's a minus 150, minus 150, 150, and here also for the other beam also I will use the same shear, minus 150, and for the moment we'll use it as 300, so 300, okay. So you'll find that these moments have been marked over here. And now regarding the connection, as you can see, as I already told you, it's basically subject to the gravity loads. The moments on both sides, okay, you can see that this is a clockwise moment, this is an anti-clockwise moment. So in this particular case, we don't expect much of a failure in that web panel due to the shear. So we may not require in this case stiffening of this web splice or the web part by the addition of a web plate or by the use of any kind of a stiffener. So on the other hand, if it would have been a wind connection or an earthquake connection, obviously these moments would have been in the same direction, so it will be additive. The shear effects will be additive, and the web panel will be very critical. So this is a case of a gravity connection only. So we have considered the same the shear forces for both the beams, 150 each, and a moment of 300 kilonewton meter. Okay, so having done that, it's the time that we start checking this connection. So as already specified very clearly in the tutorial beginning, we have two objectives here. First, to check this connection, to verify this connection for this given load of a shear B equal to minus 150 and My is equal to 300 kilonewton meter. And the second part will obviously see, or it will calculate what would be the actual moment carrying capacity of this given connection. So basically we have to generate two models here. So let us start with this model and obtain the calculation to see whether the given arrangement is good enough for the Pz and My values. So let us start calculate. So as you can see, okay, the plates, the strains in the plates is only less than 5%, is 0, and the bolts, it's the utility ratio is on the order of 65%, and the welds it is 88%. Okay, so let us quickly analyze the model just to see which of the components are critical, etc. So what we can do is that we can just press the check button that will provide us all the strain as well as the stress distribution. So let us go straight away start with the plastic strain. So in the plastic strain, let us just mesh it so that we'll come to know what exactly. So look here, because a critical review of the analysis results is a must, and we need to see which of the components are critically stressed, and whether any kind of a reinforcing is required for those components or not. So as you can see, you can just see this model. So look here. So we are finding that a particular part of the web, near the top and the bottom compression flange, it's a highly stressed. So you can see that the development of, or the initialization of the higher strains around these regions in the web. And just here. So here we find that the web is a critical zone, and at the same time we can also see that in the flange also. Look here, on this side of the flange, on the column flange, we find that some kind of a strain development. So to summarize, we find that a small portion of the web as well as the flange near to the top and the bottom flanges of the beam are critical in this case. So that is what the distribution of the passing strains tells us. So let us quickly go to the equivalent stress. So this equivalent stress, as we have concluded from our the strain analysis. So here also the same is true. Here you will find that a particular portion of the web that is located somewhere around the top and the bottom flanges are critically stressed, and the same is also applicable to the flanges as well. So if you just rotate it, you can say that look here. So the flanges are also critically stressed, and they are taking they are going even up to a value of 250 to 75 region. So let us start just looking at the value of the bolt forces as well as the plate assemblies. So quickly, so we find that here is the analysis done for 100%, and let us quickly go for the plates. And if you find that if you just review the plates, you find that the equivalent stresses are near the region of 275. That's applicable for the column flanges. So that is what is critically, that is very clearly identified here also. So that is one important conclusion that we have. And if you see, for example, this portion, there's an end plate, some portion of the end plate, as you can see, that is located near the beam flanges. They are also taken to a higher stress levels of 212.7. Let us go straight to the bolts. Now regarding the bolts, what we see is that as it's an end plate moment connection, our bolts will be critically identified through their tension capacities. And if you see here, you will find that the utility ratios of the bolts in the tension that is going to the region of 64.8 here. So let's see how the distribution of the bolt force has happened. Here you'll find that it's a smaller one. It's near the top flange, but it's a little slightly away, and it's a 35.6. And you'll find that the bolts that is near to that, the top flange, that is a critical bolt for us. And you find that the utility ratios are almost 64.8. That is somewhere here 64.9. You may have some bolts with that ratio, so that's here 64.9. So you find that the bolts that's located somewhere around the top flanges are going to be critical. And going to so look here. So if you see the bolts that is located in the bottom one, you find that they are subjected to almost zero tensile forces. So this could also explain the reason why we normally use such bolts for taking the shear loads, and the top of bolts indirectly taking the tensions. So that is readily substantiated through this analysis. So, and regarding the wells also you will find that some of the wells are critically utilized. For example, if you see here, this is one such area where where the flange is connected. It is taken to a level of 88.2%. So having done that, we find that the connection is good enough for the applied loading. Now the second exercise that we would like to know is that for this particular case, what could be the surplus capacity that is available in the connection. So that provides a little bit of confidence to the designer. My connection has got some capacity or some surplus reserve. So in order to perform the joint design capacity, we need to change the analysis type. Look here, so far we have been talking about the plastic strain analysis, the EPS. Now it is important that we carry out a second type of analysis, that is the DR, which provides you the joint design resistance calculation. So what we do is, we want to use the same model, so we can just copy this, copy. So you'll find that, okay, the job name, project name is changed to extrusion STR1. So here we will not go for the EPS, we go for the DR, that is a computation of the design resistance. So that is about, okay, the DR. Now it's important that we start, okay, performing the calculations. And I just want to tell you that all these values, it remains the same. And remember that the Idea Statica start with, okay, to find out what would be the possible, okay, overstrength available, okay, or the reserve available, okay. Idea Statica will start with this value, and let us find out what could be the excess capacity available in the section. So we'll keep all other parameters the same, because we want to use this DR, or the joint design resistance calculation, for the same model. Okay, so let us just perform the joint design resistance calculation, press the calculate button. So this may take some time. So as you can see that the load is incremented, okay, from 100 to 174 percentage, and now the results are readily available to us. So here what we need to do is, we have to go to the check, and so here you'll find that the analysis is performed and the joint design resistance. Look here, the factor 174.5 percentage. That means they got another 75 percentage reserve. That's a good news for us. So 175 percentage. So it does mean that we have an applied moment of 300, and it can take a moment excess of it by another 74 percentage, or say 75 percentage. So this, as you can see that here is a graph, what would be the load increment, okay, versus the strain. So here we see that this factor of say 174.5 percentage corresponds to a strain level. That means any one of the component could be taken to a strain level of 2 percentage when we approach a factor of 1.74. So now in order to demonstrate, okay, what I will do is, I'll just multiply my original moment of 300 with this 1.74, just for the demonstration purpose, and let us see what could be the plastic strain levels that is getting developed in the model. So what we do is, we simply go back to the original model, okay. So what we need to do is, let us go back to the the design. So we'll increase the load here. So I'll just multiply 300 approximately 1.74. I call it as a little bit as lower value. I use it, though it is some 515, I will use a 505 for the demonstration purpose. So this is my 505. So what I've done simply is that I have increased this applied moments by another 75%. That is, I simply multiplied it by 1.75. So let us just calculate and just see what will be the structural response at this level. So look here, you can see that the bolts are on the verge. It is 98.9. Okay, and the wells are also on the verge, and we find that earlier, okay, the strains were too less, but here we find that the strains have gone up to the level of 1.6. So let's go back to the check model and just see how does the stresses, the strain distribution looks like at this higher load level. So what we do is that we just put as a plastic strain, and we just go the mesh. So look here, guys. So one thing is very clear to us, at this higher load level, can say that the strains and the stresses have spread, okay, all along the web, and the compression is getting critical. Here you will find that this area has a spread at this higher load level, and here also it has just spread, okay, all along the flange portion. So if you go for the equivalent stress, you will have a similar observation. So in the equivalent stress, you will find that yes, so many parts. So for example, if you see the web, you will find that the stresses have already reached the design stress level of 275, and you can see that the beam flanges, okay, and the end plates are also getting critical. They are as they are approaching 275 level, and the strains have gone up to a level of 1.6 percentage. So that's all about the discussion on the extended end plate. So please ensure that you subscribe to the channel so that you will get a notifications as and when very interesting video tutorials will be uploaded in the channel in the future. So thanks a lot for a patient hearing, and all your valuable comments are very important to us. So please send your comments as well.